Hi guys, this is the 8th video in this series which attempts to broaden and deepen our understanding of the origin of the laws of physics and of our physical theories. In this video I want to look at what's called a Cayley or multiplication table for our reflection operations or reflection transformations, which we looked at in the previous video. Okay, we have a set, a set of operations I, RF, X, RF, Y, and RF, 0. Okay? This here is the set of all possible reflections. Okay? Because we can think of it as a set, we use set notation. So oftentimes mathematicians will use these little wiggly brackets. Okay, and inside the wiggly brackets we write each of the elements of the set. Okay, so in our case we have 4. There are 4 possible reflections. Okay, this multiplication table is extremely useful for lots of reasons, and we'll see in a moment. But it's a nice visual representation also. Okay, we looked the last time at reflections of the point AB in 2 dimensions, okay, in the 2-dimensional plane, often called R2, where R stands for the real numbers and you have 2 of them, so it's R2 or R squared. Okay, so we looked the last time at a reflection in the x-axis, which would bring the point down here, or a reflection in the y-axis, which would bring the point over here, or we looked at a reflection in the origin, which bring the point down here, and then we have the identity transformation, which is the do-nothing transformation. Okay, so with this table laid out as it is, I want to examine what possible combinations we have. Okay, so we begin, the row is, these rows are multiplied first. Okay, that's the convention. So what happens is, we'll start with this I, and then we'll think about what happens if we do I again. So if we do the identity transformation, and then another identity transformation, that's the same as doing nothing and then doing nothing again. So it's the exact same as just doing nothing. Okay? If we do nothing and then rotate and then reflect through the x-axis, then it's the same as just reflecting through the x-axis. Okay? If we do nothing and then reflect through the y-axis, it's the same as just reflecting through the y-axis, and you get the idea. Okay? That entire row is reproduced from above. Same with this column here. If you reflect in the x-axis first and then do nothing, it's the same as reflecting in the x-axis, and so on down this column. Excellent. It gets more interesting from here. Okay, what happens if we first reflect through the x-axis and then reflect through the x-axis? So we're here. If we reflect through the x-axis, we come here. Then if we reflect through the x-axis again, we come back. Okay, so we come back to the original position. So that's the same as I again. Okay, it's the same as doing nothing. What if I reflect in the x-axis and then reflect in the y-axis? Okay, so we start here, we reflect in the x-axis and then reflect in the y-axis. Okay, we come down here. That's the same thing as having reflected from the beginning through the origin. Okay, so that is same as reflection in the origin. Agreed? Okay. What about reflection in the x and then reflection through the origin? Well, if we start with the point here, reflect in the x and then reflect in the origin, we come to here, which is the same as having reflected through the y-axis. Okay, so you can begin to see what's happening. you'll notice that only one of these elements appears in each row and each column so far. Okay, what about reflecting in the y-axis and then reflecting in the x-axis? So y then x. It's the same as reflecting in the origin. Reflecting in the y and then reflecting in y. So that's reflect in y, reflect back in y. You end up back in the same beginning position. Reflect in the y-axis and then reflect in the origin. Well, that's reflect in the y-axis and then in the origin. You end up at the reflect in the x, which I could have seen anyway because it was the last one left. Okay, reflect in the origin and then reflect in x. So reflect in the origin, then reflect in x. Sorry, that's the same as reflect in y. Reflect in the origin and then reflect in y. So reflect in the origin, reflect in y. You end up in reflect in x. And then the last one, well, the last one has to be I, just looking at it, but it's obvious because if you reflect through the origin and then reflect back through the origin again, you arrive at the same position. So you can see quite a few things here. Okay, you should notice quite a few things. The first thing I guess you would notice is that each of these elements are their own inverse operation. Okay, by which I mean if you reflect in the origin and then reflect back through the origin again, it's as if you did nothing. Okay, so they're their own inverse in a way. Okay. One other thing you might notice is that this multiplication table is closed. What do I mean by closed? Well, closed means that at no point when I multiplied or combined these reflections, at no point did I leave this set. I didn't need to describe combinations of these in any way other than what I already knew about. Okay, so these are the only four operations that appear in the entire table. Nothing appears from outside. So we say that this table is closed. Okay, or this set is closed. Okay. Another thing you might notice is this, that this table is symmetric. It's symmetric. And what I mean by that is if you draw this line across the diagonal, the bottom half, the bottom pyramid, or the bottom triangle, if you like, is reproduced exactly above in the second half. Okay, so you have RFX, reflection X here, reflection X here, reflection Y here, reflection Y here, so it's mirrored. Okay, it means it's symmetric. We call this symmetric. Okay, and what that really means, if you think about it, is this, that reflection in the X and then reflection in Y, which gives you reflection in the origin, that's the same answer as if you first reflected in Y and then reflected in X. You still get the same reflection in the origin. In other words, what that means is that AB equals BA. So if you do A first then B, or B first and then A, and then do the opposite, you get the same answer. Okay? So if you do reflection in X, then reflection in Y, you get the same answer as reflection in Y, then reflection in X. If something has this property, this is known as commutative. Commutative. Okay, so we would say that this multiplication table is commutative, or this set is commutative. Okay, so what's interesting about this is that this pushes us towards the idea of a group. So group theory in mathematics is related to symmetry. It's the language in which you describe symmetry. Okay, so in the next video we're going to examine the definition of a group, and you'll see that it has quite a number of these properties.